So today's webinar will be focused on explainable AI, which is a very hot topic today. And we are really happy to welcome our speakers, Martin Tamajka and Jan Čegiň. They are from the Kempelen Institute of Intelligent Technologies, which is mostly one of the leading institutions in the AI research field in Slovakia. So we are very happy that they are able to be here today with us and to bring this topic to a wider audience. So thank you. That's all from me. And now I would like to hand over to Martin so that he can start sharing his presentation. One more thing, maybe if you want to ask any questions, please leave them in the chat, and my colleague will later on, after the presentation is over, read them, present them, or you can even raise your hands and ask them. So thank you.
Oh, sorry, I was muted. So first of all, thank you very much for invitation to this forum. I believe it is very important to share the information and experience in the field of AI and development of AI. So I'm really excited to provide some of the insights about what we are doing in KINIT, which is the Kempelen Institute of Intelligent Technologies, and how we use the Slovak HPC and how it actually enables us to do research in AI in quite a lot of fields. So let's start. To introduce us, we are both from Kempelen Institute. Kempelen Institute is dedicated to do top-notch research in AI. We are focused on quite some domains and quite some areas. And currently, today, there are two of us, Jan Čegiň and me. Jan is from our web and user data processing team. His focus during his PhD studies is on data augmentation, crowdsourcing via large language models, and NLP in general. I am leading the research engineering group at KINIT, and I'm also a part of the NLP team, which means that I'm also quite in touch with NLP. Besides that, I'm also interested in AI and machine learning, and research-wise, I'm oriented on explainable AI, and in the past on computer vision, especially in medical imaging domain. So today's outline and today's presentation will be divided into two parts. In the first part, which will be more about presentation, it will be more like a lecture. We will focus on explainable AI. We will cover multiple aspects of this, in my opinion, very interesting and growing field in AI. And in the second part, we will focus on how we actually use the HPC in particular research problem at KINIT. We use the Slovak HPC and other HPCs for different purposes, but we will demonstrate it on one particular. And we will also provide some really hands-on demos on how to use those, especially Slovak HPC, how it can be fit into your daily workflow. And also, please really be interactive. I will have some questions on you, so do not hesitate to speak anytime. Let's make it interactive. Let's make it fun. And now let's start. Let's dive into explainable AI. And the first slide is, and I'm sorry, I will annoy you maybe, but the first slide is a call for interaction. Does anybody of you know this picture, or who could be in this picture? And please feel free to speak.
Hi, I know only horse. There is a horse.
Yes, and
I do not recognize any people there.
Okay, and can you say something about the horse?
It's black. I think it's male. Nothing else. No.
How about the name of the horse?
Name of the horse?
Yes.
No idea.
Okay, so this is actually one of the most famous horses in the human history, and his name was Hans. The clever Hans, or by his original name, der kluge Hans. And this was quite an interesting story behind this horse and his owner, which was Wilhelm von Osten. In the beginning of the 20th century, there was this horse, and he and his owner performed quite a show. They basically had some show with the horse. So the story is that the horse was considered to be really clever. The owner of the horse claimed that the horse can do some basic math, that the horse can recognize and remember what day in the month it is. He could even do some more advanced stuff. So the people were wondering how it was actually possible that the owner, Wilhelm von Osten, wrote some mathematical equation on the table, and then the horse was able to answer the question. So for instance, there was an equation 10 plus 2 equals, and the horse was, and then what happened was that the horse was tapping with his hoof until he tapped 12 times, exactly 12 times the right answer to the equation, and then he stopped. And he did it for quite some mathematical equations of different types: multiplication, addition, subtraction, and so on. So people were wondering how is it actually possible that this horse was so clever, that he could understand math. So they started to investigate this, and there was a guy called Oskar Pfungst who actually found out the answer. And I believe you would not be surprised when I say that the horse was not that clever. The horse just discovered a very nice shortcut, how to always get to the right, or almost always get to the right answer. And the trick was that once the owner of the horse wrote the equation and the horse started to tap his hoof on the floor, the horse actually observed the reaction of the owner and of the audience. And when the right answer was 12, when the horse was closer and closer to the number 12, then he observed that the people started to hold on their breath because they were so excited. They were expecting whether the horse will stop tapping the hoof or not. And when the horse observed that the people froze, then he stopped. So the horse basically discovered some shortcut, or in our vocabulary, some noise in the data, and he managed to use it. And now maybe the question is how this is actually connected to the explainable AI and to AI in general. So let's discover. Let's start with a warm-up exercise and motivation for explainable AI. Let's suppose that we are in a situation that we have two classifiers. We have the task that we want to perform, quite common task. We want to perform image classification, and we have two classifiers. One of them is convolutional neural network. The second one is a classifier based on Fisher vectors. And so we start. We have this classification task. And what we want to do is we want to classify images from dataset like CIFAR or ImageNet into different classes. For instance, boats and horses. So we curate our dataset, we train the classifiers, and then what we observe is something like this. When we evaluate the classifiers, both models have approximately the same performance on training data, on validation data, on testing data. So there are not some significant differences between them. And now the important question is, when we have such a situation, how can we decide and how can we estimate in some reasonable way which of these models will perform better in the wild, in practice? So what, in your opinion, could help us to decide? Any ideas? Okay, I will not be so bad because I know it's already quite late. So the usual stuff that you could do is that you can use, for instance, additional metrics. If you compare the classifiers based on their performance in terms of accuracy, then you can, for instance, compute precision, recall. You can compute F1 score. And maybe these will provide you some additional insights into the behavior of the model, and you can estimate how they will behave in the future, in the wild. So these are very valid options. you can also use additional data. So if your data was not able to distinguish between the performance of these two models, you can collect additional data. It's, again, a very good approach, but it can be kind of costly because collecting data tends to be kind of costly. There is another option. If you did all the above mentioned things and the models still seem to be more or less the same, you can roll the dice. It can be a very valid approach. If you cannot decide on the models, you can roll the dice, or you can do some sort of A/B testing. You can decide based on the size of the models if the performance matters. But also what you can do is that you can use explainable AI to dive deeper into the models and to explore their behavior on a deeper level. So let's suppose that we have exactly the same situation, two classifiers, Fisher vector and CNN, and we want to classify images. What we could use the explainable AI for is that we look at the behavior and the decision-making process of the classifier. And as you can see, now we can see the difference. We have this image that was classified by both Fisher vector and CNN classifier. And what we can see here is a sort of a heat map. And this heat map expresses, in like normal speaking, what the model is the most looking for or looking at. And we can see that the Fisher vector classifier, at least for these two images, looked mostly not on the ship, but at the ocean. Compared to that, the CNN classifier was more interested and put more weight on the ship itself. So based on these two images, we could get quite suspicious about the Fisher vector classifier, because this is something that is kind of similar to the Clever Hans problem. And so what we can do is that we can take the whole training set, the whole testing set, or validation set, and we can compute some kind of a average heat map. And now we can see quite definitely that the Fisher vector classifier has cheated quite a lot. So the Fisher vector classifier decision-making process was very likely like, if there is an ocean, if there is some water, then there is a ship. So I will make a decision based on that, which is not good because the water doesn't have to necessarily be connected to the ship. And also, if I wanted, for instance, to distinguish between classes ship and fish, it would be a real problem. So based on the use of explainable AI, I can get completely different insights into the model, deeper insights into the model. And I, in this case, would select this one because it seems to make more reasonable decisions. And this is actually what we call in the domain of explainable AI or AI in general, a Clever Hans behavior. The model basically found some shortcut, found some noise in the data, not necessarily noise, but often it is a noise, and it used it. This is another very famous and very nice example of Clever Hans behavior when, again, two different models, Fisher vector, deep neural nets, were trained on exactly the same data set, but the Fisher vector classifier discovered this guy in the images. So it discovered correlation between the presence of some watermark and some class. So if it saw some watermark, then it classified the images as horses, which is, again, not a clever behavior, but some models tend to do this. So this was quite a strong motivation behind explainable AI. And what I would like to depict is that the explainable AI is, of course, used to explain the decisions of the models to the users so that they do not feel like they are interacting with some black box, but it can be also used to explore the models. It can be used to develop better models. It can be used to detect some hidden flaws and hidden cheating in the models. So explainable AI is useful. That's the take-home message. And now let's dive directly into the explainable AI more deeply. As you all know, since the deep learning revolution started in 2012 approximately by publishing the AlexNet network that won all the competitions with images at the time, we observe quite a strong onset of deep learning models in almost all the domains. So we can conclude that the deep learning and complex models and functions in many individual separated tasks outperform or are at least comparable to humans. On the other hand, it doesn't come at free. The complexity of the models also means that the understanding of the decision-making process and decisions of the models is complex as well. So we have better performance, but at the expense of higher complexity. And one of the ultimate goals of explainable AI is to preserve the performance of current deep neural models while increasing the transparency of them. So I believe that all of us kind of intuitively feel the difference. For instance, take the decision trees, which is quite an old type of model. And what is nice about this model, even these days, is that even if you do not completely know how the learning process and decision-making process in the model works, you are definitely able to understand its decisions. So in this case, the model case is that there is a person which is described by some 4 parameters, age, income, and so on. And this decision tree is used to decide whether the person should be eligible for getting a loan. So, and now you can see quite simply from the decision tree that, for instance, if the person ended up here in this leaf, you can quite clearly see why this decision was as it was. Because the person is older than 40 years old and the net income is higher than some threshold, so okay, we will approve the loan. On the other hand, when we have, and this is a very, very simple neural network, when we have a parametric model, it's not so easy to understand the decisions. Why? Because as the inputs, we have individual pixels, for instance. But how do we know exactly why the model assigned this probability of this picture being a car? Was it because of this neuron? And what actually represents this neuron? So it's not easy to understand and to explain the decision-making process of such a complex model. So we could conclude that we could draw some line between non-parametric or parametric models or some simple and complex models, but it's not that easy. Why? Because we can have exactly the same family of models like decision trees, and we can make it very quickly non-transparent and not so easy to explain, just by growing its complexity. So explainability is not only about explaining those big neural networks that we have right now, it can be also used to explain the decisions of arbitrary complex models, not only neural networks. So again, take-home message, it's useful for different families of models. So what we actually can understand about complex models, like for instance, neural networks, is their mechanics. We can exactly know how the outputs were calculated. So we know there is some matrix multiplication. We know there are some mathematical operations. We know the learning procedure, that's probably some gradient descent was used. So we definitely understand the mechanics. What we do not understand in some human understandable way is that, for instance, what knowledge does the model contain? Which is pretty exciting question when you think about it. So we do not know what the neural network that we trained on our training data actually took from the training data. If it is a classifier, do we know whether the model modeled like what the human face looks like, or does it classify human, or does it distinguish humans from animals based on some weird features? We do not know where the knowledge is stored. When we look at the neural network again, we can assume that the neural network somehow modeled that there is a concept of a wheel of a car, but we do not know which neurons actually represent this concept. So this is the second unknown. And the third unknown, and I will focus on this one particularly in this presentation, is why a particular decision was as it was. So if I have a neural network that classifies images, and it tells me that there is a car in the image, without explainability, it's quite hard to say why the classification was done this way. Was it because there were wheels? Was it because there was, I don't know, the glass of the car? Or was it because there was just the road on the image? And explainability can help us to answer more or less all of these questions, at least to some extent. So I used a specific word explanation quite a lot, but I didn't say what actual explanation is. And I'm sorry, but I cannot answer it by some simple answer. Explanation is something. And this can have many different forms. I will mention some of them in the following slides. But for now, the explanation is something that is understandable to humans. So it's not some huge equation. It's something that we can understand. And it also describes the behavior of the model. So it's not something that only we can understand, but it's also something that is faithful. Yes, and in this presentation, as I mentioned, we will focus on explanations of predictions of the models. And I mentioned this explicitly because explainability is quite a wide topic, and we can focus also on questions like, okay, what knowledge is hidden inside the model? This is not of the interest of today's presentation. It's just for you to know that the explainability can address quite some issues. So now in the following slides, let's focus on these two questions. How can we get the explanations, and what can be the explanation? How can it actually look like? So let's look at an example of a black box AI model. You can imagine, for instance, some VGG or some ResNet here. So some arbitrarily complex neural network, which we can definitely consider to be a black box. And from this neural network, we want to classify images. So one quite natural way how to get the explanation for the prediction is just to force the model to give you also the explanation. It's quite natural, and it works to some extent. Maybe even a better example that you can imagine even better is ChatGPT. When you provide in the prompt the instructions to the ChatGPT that it doesn't only have to provide you the answer, but also the explanation of the answer, this is exactly the case, that you basically build in the functionality that will allow you to extract explanations directly into the model. It has some problems. As you know, sometimes the models are wrong. So here in the prediction side, there is some error. And also in the explanation side, there will be some error. And this introduces another type of error. What if the prediction on its own is correct? The explanation looks correct, but the explanation actually doesn't explain the prediction itself. So it has some problems. It's definitely useful, but it has some problems. There's also another alternative way how to provide explanations, and it works like this. So again, we have the black box model, and we have the inputs, and we have the outputs, the prediction. And we will leave this as it is, the good old workflow of machine learning. But what we do then is that we take an explainability algorithms, we feed it with the data that we want to explain, the model that we want to explain, and the prediction. And then we use this explainability algorithm to extract the explanation. And don't worry, I will have multiple examples of how these algorithms can work. Just the workflow is like this. And when we are talking about this particular example, that we will use some separate explainability algorithm, we are talking about so-called post-hoc explainability. And in this presentation, we are going to focus on this because it's also the main focus of our research. And this is called, for instance, ante-hoc explainability. Again, I will repeat, anytime you have any questions, please feel free to write them or just speak up. If there is nothing, then we can move on with post-hoc explainability. Again, quick recap. We have the setup that we have our classification pipeline, for instance, and once we have the classification decision, then we want to apply some explainability algorithm to get some explanation. And one type, and now we are going to the forms of the explanation. One type of explanation is that we basically provide evidence or examples So we have a model, and this picture was classified as a mountain. And now we ask the explainability algorithm that, okay, but why? And the explainability algorithm will provide us similar data from the training set that to some extent explain why the model made this decision. And the similarity, when you think about it, you get absolutely this without any explainability algorithm from algorithms like k-nearest neighbors. But the similarity doesn't necessarily have to be taken from the similarity of the data themselves. It can be calculated based on some inner representation inside the model. So in other words, the explainability algorithm will provide you similar examples based on how the model handled these examples. And this gives you some clues about the behavior of the model. So this was one form. Another form is very natural to humans, and it is explanation in natural language. And this is probably the easiest one to be consumed by humans. Okay, examples are also easy, but this is very explicit. So in this case, the classification that the image is a mountain could be something like, okay, so there is sky and there are rocks and they are covered by snow. Therefore, I think it's a mountain. And the explanation can look like this. And now let's go to a very interesting and I believe useful kind of explanation, and it is relevance attribution. In this case, we want from the explainability algorithm to highlight those parts of the input that the model used for the prediction the most. So this was exactly the example with the Fisher vector classifier and CNN classifier, that we want from this explainability algorithm to create some kind of a heat map. In images, it's a heat map. When we have a text classification, then from the explainability algorithm, we want to highlight, for instance, the tokens or words that the classifier considered the most during the classification. So these were the forms of the explanations. There are many more, but let's focus on this one. And now let's focus on relevance attribution and one particular example. So let's suppose that we want to train a classifier to classify sentences based on their sentiment. So we want to classify sentences into 5 classes, from very negative sentiment to very positive sentiment. And we have 2 examples here. So we have our black box model, and this sentence was classified as very negative. This sentence was classified as very positive. And these are some reviews of movies. So what we can now tell about this black box model was how the predictions were calculated. This is what I already mentioned, that we know that there is neural network, there are matrix multiplications and so on. What we cannot say was why this particular sentence was classified as negative. So we can see that the classification was probably correct, but we do not know why. So what we can use is, of course, explainability. So our goal is to identify those words, for instance, from this sentence, that pushed the model towards prediction, either towards either towards the prediction or against it. So we can also identify the word that voted, let's call it this way, for this sentence to be positive. And this later we can use, for instance, to fine-tune the model if we identify some bad behavior. And what we will get in the end is something like this. So from this, we can immediately see that the words neither, nor contributed to the prediction that this sentence was classified as very negative in terms of sentiment. On the other hand, funny, suspenseful voted in favor of this sentence being positive. But as you can see, the prediction was correct. So it means that these words were given in the classification process much higher weight than the other words. And exactly the same holds true for this one. So these were the forms of explanations and one particular example. And now the question is, how actually from this setup that we have the inputs, outputs, and the black box model, can we get the explanations? Any ideas? Even stupid or simple ones, just any ideas? Okay, so let's move to them. A very simple algorithm could be based on occlusion or ablation. It depends on the implementation. So the idea is that we have the classification, we have the inputs, we have the outputs. And now what we can do is, based on the relevance that was attributed by the explainability algorithm to individual parts of the inputs, we can remove parts of the inputs and observe what will happen with the output. And that's the whole idea. And now the idea is that if we remove the most important part that were, or for instance, in the image, if we remove the most important pixels from the image that were really important for the decision, then the confidence of the classifier should drop significantly. This is the whole magic. It's very easy to implement, and you even do not need to know the structure of the model itself. You still handle the model as a black box. So it's a very nice method. And this is actually the benefit, that is easy to implement, and you can apply it to more or less all the classifiers and all the models you know. But there are also some problems. And one of the problems is that when we are talking about occluding individual input parts subsequently, it means that we also need to perform the inference many, many times. Because we want to, for instance, hide only 50 pixels at a step at a time. And if we have a full HD image and we want to always only hide 50 pixels, then we must perform maybe even thousands of inferences with the same input. So computationally, this is very expensive. If we want to target this problem of computational complexity, there is no easier way how to use sensitivity analysis. So what sensitivity analysis does is that it takes the input, computes the output, for instance, through the neural network, and then it computes the gradient of the output with respect to the input. So we use exactly the same backpropagation algorithm like you use to train your own neural networks. So again, the benefit is it is extremely easy to implement in modern frameworks like PyTorch. On the other hand, it doesn't tell you what the decision was actually made based on. It will only tell you what the decision is sensitive to, which is a little bit different answer. So these were just two very simple algorithms how to get explanation for a classifier or for any arbitrary model. And now let's look at some more robust and more complex algorithm. And one of these is so-called layer-wise relevance propagation. And it's very clever. It's also theoretically based, which doesn't hold true for many explainability algorithms. And also it's quite commonly used these days. So the idea is like this. Let's have a classification task and let's classify again images. So we have a convolutional neural networks with some fully connected layers in the end. And we want to classify an image like this, for instance. So we have the trained classifier, we perform the classification, and we have this score. So the winning class, which represents dog, got the score 0.91. So high probability that there is a dog. But what we also want is the justification or explanation of the decision. We want something like this. We want to highlight the input features, the parts of the image that contributed to this classification. And now we can use either one of the two methods that I already mentioned, or we can use layer-wise relevance propagation. And the LRP, the procedure, is really clever. what it does is that it takes the output of the neural network and it redistributes it back through the neural network, but not through gradients, based on how individual parts of the network, for instance, how this one particular neuron, contributed to the prediction. So if this voted very strongly in favor of this prediction, then it will get a big chunk of the class. This neuron didn't contribute to the overall prediction that much, so it only gets some insignificant chunk of the relevance. And if we apply this rule, this propagation rule, recursively throughout the network, then we will get back to the input. And here, what happens is exactly the same thing. We will assign individual pixels or individual input features as much relevance as they contributed to the final prediction of the model. So in the end, what we get is something like this. And what happens inside the layer-wise relevance propagation algorithm is something like this. There is this equation, do not worry about it. The only idea is that I want to redistribute this guy, this number, to the previous layer, so that the sum of these numbers, sum of the contributions, stays exactly the same. It's called conservation property. And I want to do this recursively, back to the inputs. So what I get in the end is this guy. I get this heat map. But it's not the only thing that is interesting, because I can also say, for instance, how relevant is this particular neuron for a particular class. So I can model how often, for instance, this neuron contributes to class dog, how often it contributes to class sheep. And then I can, for instance, detect some weird behavior in the classification process. Let me give you an example. If an image that contains a sheep is classified as a dog, I can explore the inner behavior of the classifier, and maybe I can find some patterns. So this is one of the very nice algorithms. You can find a very nice demo of this algorithm, very nice implementation by its authors from Fraunhofer and TU Berlin at heatmapping.org. I will skip this slide, but I will look at this one. So we have a task which is kind of interesting. It's a multimodal task, visual question answering. So, and what this task is about, that it's basic. I have an image, and I would like to type a question about this image, and I want the multimodal model to answer my question correctly. So let's look at it. So I typed a question: what kind of an animal is there in the image? And the model provided the right answer. Okay, so the answer is right. And now I would like to know what the answer was actually based on. And it's nice to see that explainability is not bound to a particular domain. It's not bound to NLP. It's not bound to computer vision. It's also usable in multimodal domains. So it can highlight me the parts of the image that were considered important, and also the part of the question that were considered important. And again, I can, through this, explore the behavior of the model and maybe identify some cheating in the model. So this was it, the basic about the explainability. And now, when you have some idea about how the explanations can look like, what the explainability is good for, let's look at what actually means to have a good explanation. And also, let's look at some ideas how to measure the quality of explanations. So, as I mentioned before, explanations is something that the humans should understand in most of the cases, not in all of them. But let's keep it this way. And also, it should provide you the right answers about the behavior of the model. So based on the literature, we can identify two components of a good explanation. A good explanation should be understandable to humans, and it should be faithful. It should provide you the right clues, the right answers about the behavior of the model. And the thing is that you need to quite carefully balance between these two properties. And the reason is that it's quite easy to get explanations that look very nice. So for instance, here, there was a picture and I classified the picture and the classifier provided correct answer that there is a parrot. And the explanation looked like this. So it highlighted some parts of the parrot that definitely, I would say, with my human eyes are important for the classification task, because you can see it's the head of the parrot and some parts of the wings. But it hasn't shown me the full answer about the behavior of the model, because I know that also this head of this parrot contributed to the prediction. How do I know it? Well, because I manually removed the part of the explanation from the image. But it looks pleasing because the explanation is quite compact. It isn't something like a noisy image, and it seems to be persuasive. But it hides some parts of the behavior of the model. On the other hand, I can have an explanation that provides me all the details about the behavior of the model. It highlights all the pixels, even if they contributed to the final prediction by tiny, tiny part. But then it's harder for the humans to understand. As you can see, most of the image or most of me and the parrots are highlighted in some way. So maybe for humans, it's too much information. So we need to find some sweet spot in between where nothing is hidden, but there are not unnecessary details. So to sum up, a good explanation should balance between two components, understandability and fidelity. And to make it more confusing, in the literature, you can find it under very different names, these properties. But this is how it is. And now we know what an explanation is, how it looks like, what are the properties we want from our explanations to have. And the important question is, how can we actually measure the quality of explanations? How can we measure understandability and fidelity? So let's say that we have a black box model. The ground truth for this image is that it's a frog. The the prediction is that it's a frog. That's cool. And the explanation is like this, which seems to be reasonable. And the question is, how do we measure the fidelity and understandability? Because in the end, we want to quantify somehow how good the explanations are. Okay, I will get to that later. And now one model example when explanation can help us, and then I will move to measuring the quality. So let's suppose that you are an administrator on a blogging platform. So you have a discussion forum, and these days, I'm quite sure you are aware of it, the blog fora and the discussion forums are full of hate. It is as it is. And the role of the administrators is to somehow moderate the most hateful blogs. And if necessary, if it is really too hateful, then even maybe remove the blogs or at least hide them. So this is the admin's job. And of course, we can use AI to help us. So we have an algorithm that somehow scans the thousands of blogs that are added to the platform every day. And only a selected part of the blogs are marked as containing hate speech, and they are passed to the administrator. But still, if it is only 100 of blogs a day, it's quite a lot of work to go through them. And now the task of the admin is, because now no AI is perfect, is to read these suspicious blogs and decide whether it is confirmed hate speech and it should be deleted, or whether it was a false alarm and then no action is needed. Why? Well, because we have freedom of speech, so letting algorithms do the censorship of the blog platform on its own, it's kind of dangerous. And this is tedious. If one blog has, for instance, 1,000 words, it means that the administrator has to read quite a huge amount of text to this site. So we can use explainability to improve this even more. So in this setup, the admin only has the texts and the suspicion that there is hate. If we use explainability, we can, for instance, provide this administrator some clues why this particular block was detected as containing hate speech. And if we highlight only those parts that contributed to the prediction of the document being tagged as hate speech, then we can actually save the administrator quite a lot of time. Because if this really was a hate speech, and for instance, this one sentence would contain words like all Ukrainians should be killed, the admin doesn't have to read all the block because immediately he sees, okay, this is hate speech, and all the around can be just a fluff, but there is definitely some strong hate. So it is confirmed, it should be deleted. So we can use the explainability to even more improve the basic AI workflows. This is another use case. And this can be used to, this can be also connected to measuring the quality of explanations. How? So let's suppose that we provide one administrator explanations from algorithm A. So what we can measure is how quickly an administrator is able to decide for one block on average, whether it is false alarm or not false alarm. And we can then provide another administrator or the same in another day with explanation extracted by algorithm B. And then we can just measure the time, how quickly or how much these explanations help the administrator, and we can compare. And this is actually one of the most important and one of the strongest way how to measure the quality of explanations. Of course, we are computer scientists, so we would like to automate as many things as possible. So there are different other automated ways how to measure the quality of explanations. So one of them is based on quite clever idea, and which is similar to occlusion analysis, and it's called pixel flipping. So the idea is that we first compute the explanation and identify those words and tokens, if we have, for instance, sentiment classification task, that contributed to the final prediction the most. So right now, the model has at its disposal the full sentence or full review, and the confidence of the prediction of the model is 1. So it's completely sure that this is negative review. So what we can do is that we start at the starting point. The model is completely confident. What we do now is that we remove the word that was marked by the explainability algorithm as the most important. So we remove the words terrible and this one. And what we can see is that the confidence dropped a little. Then we continue. We remove the second most important word, total crap. And we can see that the confidence dropped, but now it dropped quite a lot. And we do this sequentially, one step at a time. And through this, like you can see, we can do this for different explanations and different explainability algorithms. And we can observe how quickly the confidence curve actually dropped. And the best explainability algorithm in terms of this metric is the one that drops almost immediately down. Okay, this is something that I already mentioned a little bit. So we have the case with the two humans, and we want to measure how much the explanations help the human to fulfill their task. So we can measure difference in accuracy, difference in time. We can measure basically anything that we consider to be important. Yeah, this is it. These were quantitative measures. So we objectively, quantitatively measured how much these explanations help the humans. But the thing is that the explanations are given to humans often. And we do not only need to quantitatively measure how much they help them, because humans are not robots. We only need to make qualitative measurements. So we need to also be careful and ask the humans how satisfied are they with the explanations. Because if the humans are not happy to use the explanations, for instance, it's too much information for them, then they will become frustrated, and in the end, the explanations will not help them that much. So we can basically ask the humans through questionnaires. The risk is that it's more subjective, but it is what it is. Yeah, and this was it for the explainability part. Thank you very much. And maybe if you have some questions for this part before we skip to the second one.
I don't think there are any questions in the chat, actually.
No, in the chat there are no questions, so I think that we can proceed to our second speaker, Jan Čegiň, who I welcome here, and I think that without further ado, you can start your talk.
Thank you very much. Martin will handle the slides, please, for the time, and then we will skip to the demo. Actually, there is one question, so maybe Martin, you can answer that. One popped in, and then we can proceed.
So I don't know if Martin can see the question, actually, if he's sharing, so I will read it out loud, or Stefan, you can ask it yourself and unmute yourself and ask it yourself.
So I wanted to ask, in case of some model used in a publication, if there should be also a part given for the explainability of the model, because sometimes you can find publications where something is predicted by using a neuronal network, but also the authors know that this is just a black box and they have no idea why the model was sorting the data as it has done.
Okay, I believe it would be nice. It's definitely not happening right now. And if you ask me, well, I would divide the answer to two parts. If it is, for instance, a paper of a type that there is a competition and people are basically creating models to beat up the competition, then I think explanations could be of great value, because often the differences between different classifiers are not distinguishable in terms of statistics. It could have been caused by chance that one classifier was better than the other one. Then the explanations, I think, could be very strong. But in terms, well, now imagine that you develop a completely new model with a very complex architecture. Then it is possible that there is no reasonable explanation algorithm that you could even use. So in that case, I think it would be very complex, or even, well, it would be very difficult to ask from the authors of the papers to provide also explanations. So I'm not sure whether I answered your question, but in my opinion,
and in case that you are developing a neuronal network model and you have to use 2/3 of the data for learning the model, and you can predict 1/3 of the data with an acceptable result, would you consider this as a good model, or the 2/3 for learning is too much?
I'm not sure whether I understood. So the question is, if I used only 1/3 of the data to train?
No. You are developing a model and you use, let's say, 66 data sets, and the remaining 33 will be used for checking the model performance. Mm-hmm. And if you need, as I told you, 2/3 for data for learning the model to make the prediction, would you consider this as a good model, or perhaps my question is stupid? I don't know.
I would say very alibistically that it depends if, oh, it depends, but generally what I would do in this use case is some kind of k-fold training. So I would evaluate the model better. So, you know, so that I will always use some different subset of the data sets or data points to train the model, evaluate it on the rest and move on. But I'm not sure how this is connected to explainability.
So I asked this question because I made a mechanistic model which was based on physical principles, and I used just a very small amount of data, and I got quite a nice correlation with the real data. And it was just a question: how can I really assess if a neuronal model is good enough? Or where are the thresholds when I can say that this model is really performing, let's say, good enough?
Mm-hmm. Okay, so for the thresholds, I have no idea if there are some, but how you could use the explainability is, for instance, you take the test data, you compute the basic metrics, and then you also compute the explanations on the test data or even on the trained data. And you also analyze maybe case by case, data point by data point, how the decisions were made. So not only if the prediction was correct for individual data points, but also whether the prediction, let's call it physically, made sense. Like whether the correct prediction was made based on reasonable input features.
But anyhow, then this part of the model evaluation should be more or less included in the presentation to really to get the information that the model is what is using for the decisions, and to see that this is really let's say has a physical relationship or physical meaning.
Yes, it would be nice. And for instance, we already made some experiment in these regards. So right now we are working on a concept that we call AutoXAI, automated explainable AI. And the idea is that we want to measure the quality of explanation at scale. So we want to measure it on thousands of data points, which cannot be done manually, of course. So what we do, for instance, and this is close to the physical meaningfulness of the predictions, is that, for instance, we have MR images with brains and brain tumors. And if the classifier tells me about the image, that there is a brain tumor in the image, so it was, for instance, a correct classification because there really was a brain tumor, but the relevance of the explanation is not concentrated in the tumor, there is something wrong with the model. Because the decision that there is a tumor and it was not based on the pixels that represent the tumor, it's weird. And something like this can be used for many different domains.
Okay, so just make it short. It would be nice to have this analysis, but not in all cases is this analysis provided, or is even possible to provide.
Yes, impossible or very difficult, or not everybody actually knows the explainability. So it's in the vast minority of cases that some explainability analysis is provided for the models. But you can find it some flavor of explainability under different names, for instance, probing for language models. It's kind-ish explainability. Also, ablation analysis. This is very similar to occlusion analysis that I mentioned today. So you can find it in minority of cases under different names.
Okay, so thank you very much, and sorry for disturbing the presentations.
Thank you very much for the questions.
So there are normal questions. I believe we can proceed to our second distinguished speaker, Jan Čegiň. So the stage is yours.
Okay, thank you. So today I'll show a little bit how we work with HPC, namely Devana, in our research. And to do that, I will first introduce what we actually do. So in our research, at least partially, we use a bunch of large language models. So what those are, everybody probably knows ChatGPT and its equivalents, GPT-4, etc. But the interesting part about this is that there is a bunch of open source large language models. So a bunch of people got together, trained some large language models with billions of parameters, and put them somewhere on the internet, mostly like GitHub, Hugging Face, etc. And it is nice to know what kind of capabilities these models have, what you can do with them, and how they influence other work. So basically, we do a bunch of stuff. For example, we investigate the stability of training with these large language models, where you can fine-tune them for your specific task. For example, you can fine-tune them to be your very own chat assistants, or I have seen even cases where you can take your own messenger history and take them to train them to impersonate your own persona on Messenger, Telegram, WhatsApp. We can use them to augment textual data. So this is an area I'm working on, where you take some sentences. For example, let's say that you're trying to predict what kind of sentence has or what kind of sentiment a given sentence has. So either negative or positive. If you are either praising, for example, a movie in your review, or you criticizing it, and you enhance those sentences a bunch of times by paraphrasing them, and then you train your classifier and how that helps. Third, we can also investigate biases in large language models. So, for example, gender biases. How often, for example, some genders correlate with, for example, some positions or jobs like nurses, where in most cases the gender language would be about women, and a bunch of other stuff that we also do that I didn't list here because I don't know everything we do in our company. But today, if we can get to the next slide, today I will show some ways how we work with Devana, namely. So we have three different modes, at least, that are useful to us. I'm not saying that there are any other useful modes of using this platform, but for us, it's mostly using SSH to connect directly to the server and do some computations there. Using the open on-demand platform, which I personally find very helpful, web-based platform where you can access all you need from your web browser, or using an IDE. For example, you can use Visual Studio plus Remote SSH to use your favorite programming IDE to directly change stuff on the server and work from there. Okay, so now we will take a look at the practical example. So we will follow a actual example from the Hugging Face platform. What is it? Company, actually, where they show how we can use an LLM to generate text and figure out sentences. So let me share my screen. Yeah, this will probably work like the entire screen. Okay, so hopefully you can see it. Yep, you should see it. Okay, fine. So what we will follow now is the generations with LLMs. So actually there is, let me just explain it very briefly how this works. So given some input sentence that we have, this goes into our large language model, basically a very complex neural network with some preset weights that have been trained, where we first tokenize the sentence into some into some array of numbers that the large language model can actually understand. This is then outputted through the layers of the large language model, and we get a probability of distribution. So the quick brown fox, what should go next, jumps. And we add it to the previous sentence, and we repeat the process until we generate a certain text or text of certain length. So for example, we want to generate 20 new tokens. So we do this 20 times. Or we can do this until an end of sequence token is generated. So for this case, so to run this on Devana, this is actually quite nice tutorial. We can use, so one case you can use, of course, is to use PuTTY to connect to Devana. So just the or let me start with actually with the more interesting part, I would say. So one way would be to just use PuTTY, but or OpenSSH. But I guess everybody has some already some experience with that. However, what is a more interesting approach of connecting to the server would be using Visual Studio Code with a remote SSH extension. So this is an extension that enables you to use your IDE to directly connect to a remote server, have those files here, and either edit them right here in this IDE or run them through the terminal. So how we can do this is by opening a remote window where we want to connect to a host via remote SSH. And I already have this option here for Devana, but other than that, you can add a new SSH host where you specify the private key you are using, the username that you're using, of course, the IP or domain name that you're using, and the port, because this is, we are connecting to not 22, but port 5522, I believe. Oh, actually, yeah. But since I already have it saved here, I can just click on it here. I get a new window where it's setting up the SSH, and I'm actually connected. So now the only thing I need to do right now is to just open the folder, and I can either start from my home directory that I have on Devana, or I can, if I'm just working on one specific project, I can go there and do stuff from there. So now I click OK, and as you can see, I'm right in. So this is my home directory on Devana, where I have a bunch of stuff, a bunch of projects that I'm working on, and I can open any directory that I want, open given script. For example, this is a augmentation script where I take some NLP augmentation methods and use them to generate augmentations for a given data set. So not using LLMs, but actually using like a random word augmentation, embedding augmentations, and other stuff. So I can run it from here. I can open a new terminal and do all the terminal operations that I would want here. So for example, I can list my Conda environments, create new Conda environments, run scripts from here, etc. But this is actually not the method I'm most often using. The method I'm most often using is actually the open on-demand platform. Let me just refresh so I'm make sure that my session didn't time out. So this platform is actually web-based, so I've been able to use it on like different computers without having to set up my SSH, generating new keys, or carrying it around with me, just by using my Google Authenticator app and whichever web browser you wish. And in here, I basically can also do some editing, as we'll soon see with the tutorial. I can also monitor the jobs that are currently running, which has been quite useful for me, and directly access the shell by using this Devana shell access, and again do all of my operations that I need here. Okay, so now to run this tutorial here on Devana, I'll be using this web platform on demand. So to do this, we actually need to install some Python requirements, because to actually get this model to run, we need to set up an environment where we have all the libraries, etc. So to do that, I already set up some. So first of all, what we need to do is to create a new Conda environment from the scratch. So we are using Conda. For those who don't know, Conda is a like package dependency environment where it always creates a new virtual environment for you, in which you can like separate the dependencies that you're using, and it makes very nice it makes it very nice for you to change between projects or different projects that you're working on, where you need different dependencies and stuff like that. So we can actually create, I've actually been playing around, so we create a new Conda environment by Conda create, and you specify the name, so exa, like example NSC, and this will create a new environment for us. If we give it a little bit of time, yes, we want to proceed. And as you can see, this has created a new environment for us. We can activate it by using this command right here, and we are in it. Now, what we need to do is to just install all of the dependencies that we need to actually run this tutorial and generate some text from our large language models. Now, to do that, first of all, what I found useful was to update the, I have some cheats here, was useful to update the Python to the newest version, or rather a new version, 3.11. So before you do any like updating, Conda will always like list all the new packages that will be installed, or we just proceed and let it run for a moment until it finishes. I can talk a little bit about this model that we'll be using, Explainable AI 7B version. So all of these models actually have a model card on Hugging Face, which is a really nice platform for different models, data sets, where you can find all kinds of tutorials and basically start any kind of NLP process that would interest you, or multimodal for that matter. So if you would like to do what Martin showed, the visual question answering, you can actually start here, find some data sets, find some models that are actually doing it, and try it out for yourself. Okay, so we actually got the new version of the Python. And now, before we install all of these fancy libraries, we need to start with the most basic one, PyTorch. So to fully utilize the GPU that we have here, the A100s, pretty powerful GPUs with 40 gigabytes of VRAM, we need to load a fitting module, CUDA module, and then install a deep learning library. So we are going with PyTorch. There are also other ones like TensorFlow, JAX, but I think that this is probably the most widely used and one of the most, friendly, let's say friendly to use and to start your journey with. So we are actually using a so we're using the current stable version for the Linux platform. We'll be installing it via pip. We're using it for Python, so you can also use it for C++ or Java if there are any people who would like to do that. And the current version that we have is CUDA 12.1. We have here 20.0. And let me just load the module. So we load the module via lmod, which is Lua modules that are available here at Devana. And I already prepared this folder, NSC examples, from which I will run all of the examples and the dependencies. So first of all, I want to install this library, and for that I have prepared a textual file with all the dependencies that I need to actually download and install Torch. So this is actually how you can edit files, which I found really useful in Devana. So you can basically it opens a small IDE for you where you can have different key bindings like default, Vim, or Emacs for whoever is feeling set today. Modes for like whatever language you're using, themes. So we can have like this Retina burning one, or we can have others, whichever you like. So this is something I found very useful to do some quick changes and run them. So let's actually run the dependencies, so we can. Oh, excuse me. Yeah, that should do it. So we can actually install PyTorch, and this will install it for us. I have already cached it in my own home directory because I'm using PyTorch for also other, or I'm using it also in other environments. If it wasn't the case, we would see that it would be start downloading it into our home directory, where basically all of the dependencies and also models that we'll be downloading, because we'll be downloading this Mistral 7B model into our local system. So they are all stored in the home directory of Devana. So while this installs, Mistral 7B is really actually powerful model that we have been using in our experiments. It's a model that actually outperforms Llama 2. Llama 2, for those who don't know, is a model developed by Meta. Facebook, Instagram, all the social platforms, and it's a model that they have been using. It's open source and actually outperforms a bigger version, nearly twice its size in terms of like performance. So if you don't want to like play around with it here, you can actually use Hugging Face to run some very quick inferences here. So you can also like run some examples. My name is Luis and I like to, and it will generate it for you, as you can see. So we can do this however we like here on Devana without using a platform specific tool. So we can do it here on Devana after the installation, of course, concludes. And for those of you who would like to also like try out different models, you can find them here in models. And there's just a bunch of stuff here for whatever task you need, but mostly you'll be interested in text generation. And here you have, so this is the Mistral B that we are using, but there's also an instruct fine-tuned one where you can actually give it instructions just like you would for ChatGPT. So you can, for example, define a role that it should play and give it some instructions. So for example, paraphrase some text, summarize something for me, etc., etc. Okay, let's take a look. Let me just hide these floating meeting controls. Yes, that's nice. Okay, so we finished installing our PyTorch dependencies, and now finally one more dependencies. These all dependencies are necessary for us to run the transformers library. So this is a library developed by Hugging Face, where you have all the, which basically wraps all of these large language models into higher abstractions that we can use more easily, and we don't have to deal with like low-level stuff. So let's just install all of it. So there's a bunch of libraries, because even as we take a look at this piece of code, we can see that we are not actually loading the entirety, we are actually loading the entire weights of the model, but we are loading them not in their full like bit precision, which I believe is 32, but we're loading it in 4 bits. Which that means is that we are really not gonna be using a lot of VRAM. We're gonna be having faster inference times, and we can actually do this on smaller GPUs. So for example, we don't need like even our 40 gigabyte GPU here at Devana will be an overkill, at least for this model. However, if you were to use a bigger model, you'll probably need like 2 or 3 GPUs, even with this quantization being active. So this is a new way of massively reducing the resource requirements. And as I have attended the conference last week about this, it seems that people are trying to push even for 2-bit dynamic quantization, which is really something to say the least. All right. Now, until this finishes, I can show you what will be running. So first of all, as I said, everything is installed into your home directory. So before you run anything using the scripts and deploying something as a job on Devana, you need to download the model to your own location. And we do this by running this example.py, where we only import the library and then prepare the model that is then downloaded to our home directory. So let me just run that. And CC example and example.py. So what this should do is that it just loads. Well, if you don't have them already downloaded, it will download the weights for the given model. It creates a new instance and it ends. That's it. That's all you need to do. And then we can actually proceed. So as you can see, it is actually loading the checkpoint chart and creating a new instance of the models. And yeah, that's all. Now we know that we have the model downloaded and ready to be used. And we can actually use it by running this example. So for example, here we have, first we instantiate the model. And then we have a tokenizer here for the given model. So it checks out. This tokenizer actually changes this text into numerical sequences that the model can understand. It then allocates those arrays basically, or matrices to CUDA, so to the GPU on which the model will be used. And then we use this to generate actually some IDs and again decode the numbers that we get to get the sequences. So for example, we have 2 sequences here, a list of colors, red, blue, and the second sequence is Portugal is, and we're gonna see, but let's change Portugal to Slovakia, and let's run this. So you actually shouldn't be running these examples here per se, in your own login node, because right now we are on a login node where we can actually use this, but only we generally just use this for debugging purposes. So if I really want to know quickly if something will work, but not for like computation, which can take days or even days. We have we've had some computation that took like 2 to 3 days to finish because it takes some time. Okay, so what did we get? We got a list of colors: red, blue, green, yellow, orange, purple, pink. And for the second sequence, we got Slovakia is a small country in Central Europe. It is a land, something, something, something. We have a token limitation, so we can actually increase it by a little bit, let's say to 30 tokens. And let's say that we want to add another sequence about Slovak research. So Slovakia is, and then we add a new sequence and we run this again. And again, we should get like, so 20 new tokens should be generated. One thing that should be noted for those who don't know, a new token does not always mean a new word. It can be that, but it's mostly like a new subword because of the way how large language models are trained. Okay, so we actually got some larger amount of colors here. So purple, pink, brown, black, white. Oh yeah, that's a lot. And for Slovakia, we got Slovakia is a small country in Central Europe. It is a landlocked country bordered by Poland, Ukraine, Hungary, Austria, and Czech Republic. And now for the Slovak research, is not only about science, it is also about the people who are behind it. Slovak Spectator is publishing a series of interviews. Okay, so yeah, it then generates and continues in its own generation process until we tell it it's enough. You can play around with it more with the setups. You can also give it some prompts, some instructions, how you would give it to ChatGPT. It is here in the generation with LLMs at Hugging Face. Right now, for the last part, as we're running out of time, I will just show quickly how we can actually run this example on Devana itself, not on this login node, but on the different nodes that are available. So we would actually use an shell, a bash shell file where we specify our account, name the job somehow. We are using a GPU because we're using LLMs. Right now, one GPU is more than enough, but sometimes for the really like large models like 70 billion parameters, you need 2 or 3. 1 hour is more than enough. This will probably not take more than 3 to 4 minutes. Then we activate the Conda, load the CUDA module that we actually need to deploy our LLMs and use them. Activate the Conda environment that we are using. Go back to our home environment and then just run the example. Okay, should be simple enough. So let's run this. So example run.sh. And what we should be able to see, so we can actually monitor also from here using SQ the running jobs. So the GPU example is running. The other jobs are some other computations that have been running for some time for our research. And we can actually also check it out here. So we have it here, example NSCC. So yeah, deployed on one node using one CPU and one GPU. And from what I've tried so far, it takes around 3 to 4 minutes to finish because, of course, there is some overload. You need to, or rather not overload, but I meant overhead. So the environment needs to load all the libraries, the model, and then you can generate the requirements that you need. And then we will get our results here in the logs. So right now 0 bytes, but when it finishes, all of the output, either being like the error output if there was some, or the just standard output will be stored here. In our general cases, what I have been using mostly is just saving pickle files. So just during the computation, just saving the different results that I have into pickle, but you can also do logging, whatever suits you the best. Now, yeah, we have still like 1 to 2 minutes till this finishes. So one of the models that I would actually recommend for you to try is a really new one. I think it's like 1 month old, Zephyr 7B beta. So this is like Mistral, the one that we are using right now, but even better, as LLMs are really skyrocketing right now, and there is always something newer and better. And it has been actually trained to better reflect human interactions. So it should be even more ChatGPT-like. And we can see it that it has quite good scores when compared to ChatGPT. So this is ChatGPT, GPT 3.5 Turbo, and you can see that it's pretty good. So I would actually, for those of you who are interested in this, check it out, play around with it, and try it out for yourself. There's also archive papers. So yeah, let's see if this finished. We'll still have some time. So I can still talk a little bit more about it. So this has been trained with a quite new algorithm. It's called direct preference optimization, where you basically synthetically simulate what a human would do or how a human would answer to your instructions, which ensures that the large language models are more like humans or respond to the instructions more like humans would. And this is actually a really, really new, fast way of doing it. And it helps models perform even better.
By the way,
So-
there is a question in the chat.
Yeah.
From Andre Luchny, whether you can try some commands.
Oh, commands. Which ones? Like, unsure.
So if you can open the chat.
Yeah, let me just. Okay. Just open Zoom.
So-
Got it.
If I understand it correctly, Mr. Luchny is wondering how it is possible that two versions of CUDA actually play together.
Let me just open. Yeah, because I'm a little bit struggling with Zoom, as is custom. If you can just read it for me, because I can't find the chat.
So first, Torch CUDA is available if you can run it in Python.
Oh, I see. Sorry. Yeah, so Python.
Yes.
And then we do import torch.
Yes.
We'll give it some time until import. And then we run torch. That CUDA available library, I believe, right?
CUDA.is available.
Is available.
Torch.CUDA. Yes.
Yeah, I mostly Google this stuff, though.
Yeah.
Don't be surprised.
Okay.
Yes. So yeah.
So then the second one is Torch CUDA current device. Then Torch CUDA device and as an argument 0. Yeah. Torch CUDA device count. And Torch CUDA get device name and argument 0.
Yeah, that should be the yes. So the A100 that we have on the login node. So there are two login nodes, if I believe correctly. Login 01 and login 02. And when you log in without specifying the login node, it will assign you randomly to either one of those. But you can also specify it when you sign in. So we would put like the name. So Jan Čegiň, in my case, at login 01, or you put login 02, or you can just leave login, and yeah, you would.
And in between there was also a response from Brian in the chat. So the message was that the PyTorch can work with older versions, but not newer. But it's fine. Thanks.
Yes. Okay. Yeah. As Brian said. Yeah. So now to the final part. Let's just see if we got our outputs, so we can check the std out, and as you can see, we have the results here. So the same results that we got in our local login node, we actually got them in running the example through the system, through the nodes that were available, and getting the results from them. So here we could just do a bunch of stuff that we would like, and gather all of the results we would want, or until our credits run out. Okay, yeah, that's it for me. A little bit more, this took a little bit more time than expected, but hopefully this was interesting enough for you to, well, try it out and play around with large language models yourself. So thank you.
So thank you. That was great. If I don't think there are any other questions in the chat, but if anyone wants to ask something, our two speakers, so now is the chance.
Hello,
And
I
see.
would like to ask something.
Okay, Vivi, go ahead.
So yeah, my question is about when you are connecting to Devana through VS Code. So I noticed that you were using a login node, but I guess that for computing you use one of the compute nodes.
Yes.
And so when you are working interactively with your code, is your session on the compute node somehow limited, or the time you can use it is unlimited?
That's a good question. I'm not sure. Maybe Branyo, who's in the chat, can say a little bit more about it. But I think it's basically unlimited. I'm not sure if there is some limit to the.
I can answer. I think you can only connect through SSH to the login node. I haven't tried like connecting to the compute node. I don't think that's possible.
Okay, thank you.
I have another question. Have you tried experimenting with AMD cards, or do you just use the NVIDIAs you have on Devana?
Oh, I've never done that. We've just used the NVIDIA cards, and yeah, I have just only the experience with NVIDIA cards. If somebody has tried them out, I would actually love to know how the state of working with them is, but yeah, never tried it.
Right, thank you.
Okay, if that's it, we can probably continue.
Yeah. So thank you very much for demo. And these are very last slides. So this is a conclusion. I think we can skip it because you already saw all of these. And there is just one more thing that I would like to mention, and it is a European activity that tries to create a platform for AI researchers. And one part of it, and actually one important part of it, is to provide an easy access to HPC, different HPCs across Europe. So maybe some of you already know this activity, AI on Demand. It started by Project AI for EU, and now it continues by the Project AI for Europe that we are involved in together with more than 20 other partners from Europe. So basically, this platform aims to create and provide access to AI researchers in Europe in order to be competitive to the US and to China to some extent. So we want to boost the AI researchers by providing them access to AI assets from different platforms in some unified way, to let them collaborate, to boost the reproducibility of the experiments and the reuse of them. So for instance, like Jana mentioned, sometimes we want to train or fine-tune the LLMs, the large language models, and it is kind of tough to make it properly. So if somebody already did it, it would be nice to reuse it using some nice to use platform. And also, last but not least, we would like to connect different compute nodes in Europe through this platform. So what we actually aim to do is that we aim to provide easy access to different stuff to researchers in this project. And there is already a new project that aims to do exactly the same, but for companies. And how we can do this is that right now we want to provide the researchers access to data, models, software, and compute infrastructure through the REST API. So in a couple of days, there will be a release of the platform, and I'm advertising it because I personally strongly believe that it can be a huge enabler in the European Union to collaborate on AI research more interactively and deeper as a research centers. Because I believe that right now the research activities are kind of scattered in Europe. So this is just an information for you that there will be something like this, and it can be kind of useful also for your AI labs. Okay, there are a bunch of other technical layers, but why I'm mentioning is it in this forum is because, as I mentioned, the platform will not only provide you the access to datasets and stuff like that, but it also aims to provide you access and unified access in the best case to different compute nodes. And from what I have the information, for instance, there is Euro HPC. We have Slovak HPC, we have Euro HPC, and it is not used to the full extent. So I would like to also motivate to use the HPC, which, for instance, we hadn't had any experience before, but once we started to use Devana, we saw that it is pretty easy to do. So one option is to use the HPC directly. Another option could be to use it through a platform like this. So just for you to know. And this is the end of the presentation for our side. And I would definitely like to thank you for being here and also for the interactivity. It is always very nice if the people have questions, if the people have comments and maybe even critics. It's very appreciated.